Hello students. So already we had started our discussion on the chapter Fundamentals of Organic Chemistry. In the last few sessions, we had discussed about the effects, electronic effects, that is inductive effect, mesomeric effect, hyperconjugation effect. As well as we had also discussed about the carbocation, carbanion and the free radicals example. In this session, we will be discussing about the strength of acids and bases. Before going for the strength of acid and bases, let us see what is an acid and what is a base. So there are three major theories that explain about the acid and a base. First theory is an Arrhenius theory. According to Arrhenius, an acid is a substance that produces H plus ion in aqueous medium. For example, HCl in aqueous medium will dissociate to give H plus and Cl minus ion. So HCl produces H plus ion. So according to Arrhenius, HCl is an acid. According to Arrhenius, a base is a substance that produces OH minus ion in aqueous medium. If you take NaOH and drop it into water, NaOH dissociates to give Na plus and OH minus ion. So hence NaOH is a base. So HCl is an acid, NaOH is a base. Okay, HCl is an acid, NaOH is a, because HCl produces H plus ion and NaOH produces OH minus ion. There is another theory that explains about the acid and the base, that is Lowry-Bronsted theory. Okay, Lowry-Bronsted theory. According to Lowry-Bronsted, an acid is a substance that donates H plus ion and base is a substance that accepts H plus ion. Let's take an example. HCl plus NH3 will give. HCl dissociates to give H plus and Cl minus ion. Whatever the H plus that has been produced by HCl will be taken up by ammonia, because in ammonia nitrogen contains lone pair of electrons. Hence this lone pair of electron will attract that H plus ion. So hence it will form NH4 plus Cl minus. So HCl has donated a proton, hence HCl is an acid. NH3 has accepted a proton, hence NH3 is a base. Okay. If you consider the reverse reaction, if Cl minus gets converted to HCl, so if Cl minus has to get converted to HCl, so Cl minus has to accept a proton, and the substance that accepts a proton is a base. So I can call Cl minus as a base. NH4 plus, if it has to get converted into NH3, then it has to donate a proton, hence it is an acid. Okay, now if you look at HCl and Cl minus, one is an acid and other one is a base. The only difference is a proton. One is an acid, other one is a base. The only difference is a proton. So a pair of acid and a base that differ by a proton are called conjugate acid-base pair. We call them as conjugate acid-base pair. So HCl and Cl minus is a conjugate acid-base pair. So a conjugate acid always contains one H plus more. Okay. Similarly, ammonia and NH4 plus, one is a base, other one is an acid. The difference is only one H plus. So this is also a conjugate acid-base pair. So what is a conjugate acid-base pair? A pair of acid and a base that differ by a proton are called as conjugate acid-base. Okay. So there is another theory that explains about this concept of acid and a base, that is called as Lewis theory. According to Lewis, an acid is an electron acceptor. A base is an electron donor. So an electron donor is a base and electron acceptor is an acid. For example, let's take an example of this. Let's take a reaction between ammonia and boron trifluoride, BF3. Ammonia contains lone pair of electron, hence ammonia donates the lone pair of electron to boron. So boron contains empty orbital. So ammonia has donated an electron, so ammonia is a base. Boron fluoride has accepted an electron, it is an acid. So according to Lewis theory, an acid is an electron acceptor and base is an electron donor. A base is an electron donor. Right? So we got an idea regarding what is acid base according to Arrhenius, Laurie, Bronsted and Lewis theory, and what is a conjugate acid base. And very important relation that you should remember is, if the acid is strong, then its conjugate base will be weak. Strong acids have weak conjugate bases, or if the acid is weak, then its conjugate base will be strong, or vice versa. If the base is strong, then its conjugate acid will be weak. So strong acids have weak conjugate bases and weak acids have strong conjugate bases. Okay, HCl is a strong acid. Cl minus is a weak conjugate base. That means HCl is a strong acid that its ability to donate proton is more, tendency to, whereas Cl minus tendency to accept proton is less. So hence it is a weak conjugate base. So weaker the conjugate base, more stable will be the anion is what we say. We will discuss about those things. So let us hope you have understood what is Arrhenius concept, Laurie Bronsted concept and the Lewis concept. Now, next. Let's take a few examples and let's try to go through this. Okay. Now, take an example of HCl. HCl when dropped into water, it produces Cl minus ion. Whatever the H plus produced will be taken up by water to form H3O plus. Okay. Equilibrium is indicated with double-headed arrows. Okay. If I write a longer arrow in the forward direction and a smaller in a backward direction, that means formation of product is favored. If I write it like this, it means formation of reactant is favored is what it says. So here product formation will be favored. HCl is a strong acid. That means its tendency to lose proton is more. Cl minus is a weak conjugate base. If you take an example of acetic acid plus water will give H3O plus CH3CO minus. So acetic acid will lose a proton, CH3CO minus. The proton will be taken up by water. So acetic acid is an acid. Okay. So CH3CO minus is a conjugate base. Now, so the arrow towards acetic acid indicates that the reaction is favored in the backward direction. That means the reaction is not favored much in a forward direction. So hence acetic acid is a weak acid because its tendency to lose proton is less, but acetate ion is a strong conjugate base. That's what I said. So its tendency to accept proton is more. That's why the reverse reaction is taking place to a greater extent. So weak acids will have strong conjugate bases. Okay. Whether a reversible reactions favors reactant or products at equilibrium is indicated by the equilibrium constant of the reaction. Okay. So let us see what is this equilibrium constant. So then you will have an idea regarding those things. Now, so consider an acid. HA. In presence of water, HA is an acid. HA dissociates to give H plus and A minus. Whatever the H plus that is taken, released will be taken up by water to give H3O plus. So equilibrium constant K is equal to concentration of product divided by concentration of reactant, that is H3O plus into A minus divided by HA into water. H3O plus into A minus divided by H2O into HA. I will take the water other sides, so it becomes K equilibrium into water. So water will be generally in excess, so concentration of water almost remains constant. So it is H3O plus into A minus divided by HA. The bracket indicates the concentration. K equilibrium into water. K equilibrium is constant, concentration of water remains constant, constant into constant is another constant. It is called as Ka, where A indicates acid because I have taken acid. So it is H3O plus into A minus divided HA. This is called as an equilibrium constant for an acid. Okay, larger the value of Ka, stronger is the acid. Larger the value of K implies strong acid. Larger the value of K, stronger is the acid. Why? Because when the value of K will be more, if the numerator is more, when the numerator will be more, if A minus is more, when A minus will be more, if the dissociation is more. If the dissociation is more, concentration of A minus and H3O plus will be more, numerator will be more and the Ka will be more. That means larger the value of Ka, dissociation is more. So hence stronger is the acid. Okay. Now let's take an example of this. Now, so the dissociation constant for HCl. For HCl, the dissociation constant Ka is 10 to the power 7. Whereas the dissociation constant for acetic acid, the dissociation constant for acetic acid is 1.74 into 10 to the power minus 5. Which value is high? This is a high value. So hence HCl is stronger acid than acetic acid. Okay. Now for convenience, the strength of an acid is generally indicated by its pKa value. So what is this pKa value? Okay, pKa is minus log of Ka. pKa is equal to minus log of Ka, log to the base 10 it is. For example, let's take an example. Think that I have two acids. One is acid A, other one is acid B. Let the Ka of this be 10 to the power 5. Let the Ka of this be 10 to the power 2. So now which is stronger acid based on K? Larger the value of K, stronger is the acid. So this is strong acid. Okay, this is weaker acid as compared to this. Now I will take the pKa value. pKa is minus log of Ka. So for acid A, minus log of 10 to the power 5. A raised to x minus 5 log 10. What is log 10? Log 10 is 1, so it will be minus 5. For acid B, pK is minus log of 10 to the power 2, minus 2 log 10. What is log 10? Log 10 is 1. So which is stronger acid? A is stronger acid. So that means smaller the value of pK, stronger is the acid. So if you are comparing the acid strength by using Ka, larger the value of Ka, stronger the acid. If you are comparing with pK, smaller the value of pK, stronger is the acid. So in general, very strong acids will have pK less than 1. Moderately strong acid will have pK 1 to 5. Weak acids will have pK 5 to 15. Extremely weak acids will have pK greater than 15. Okay, hope you're getting this. Let's take an example. For example, take an example of HCl only. For HCl, pK is minus 7. And for acetic acid, acetic acid. Okay, pK is 4.76. This is -7. So smaller the value of pK, stronger as the acid. Which is the stronger acid? HCl is the stronger acid because its pK is -7. Okay, this is how you should find it out. Okay, now, so what are the factors which decide the pKa value? There are few factors that decide the pKa value. One of the factor is the conjugate base that is formed. For example, take an example of acid Ha1 that dissociates to give H plus A minus 1. Another acid Ha2 H plus and A minus 2. So how we predict a strong acid? A strong acid is one that produces more H plus ion. So if Ha plus produces more H plus ion, so this is a stronger acid. Ha2, if it is produces little less H plus ion, so I can call it as a weaker acid. Ha after donating will form A minus. If the A minus formed after donation is strong, I mean stable, then only Ha will donate proton. See, we have Ha1. Ha1 will release a proton if after releasing a proton, whatever A minus formed should be stable. The stability of anion will decide the acidic strength. If the anion formed is more stable, then it will be more acidic. For example, let's take an example of an acetic acid. Acetic acid will dissociate to give H plus ion and CH3CO minus ion. Similarly, formic acid will dissociate to give H plus ion and HCO minus ion. So the stability of this anion will tell you about the strength of this acid. If the anion formed is stable, then the given acid will be more acidic. Why? Because an acid will lose a proton if after losing a proton, whatever the anion formed should be stable. So here, formate anion is more stable. Since it is more stable, the anion formed, so this is more acidic. So this is less acidic, and it is reflected by its pK value. The pK of this is 3.75 and the pK of this is 4.76. So now the question is, why this is more stable and why this is less stable? See, it is C double bond O, O minus CH3. It is H, C double bond O, O minus. Whatever the negative ion that is there will undergo delocalization, resonance stabilized. This also gets resonance stabilized. But the problem is, here there is a methyl group. Methyl groups are all electron donating group. So this will donate electron and it will destabilize it. See, we want someone who can accept an electron. For example, see, if there is like this. See, when this will be stable, this anion will be stable if the negative charge gets delocalized. Negative charge should get delocalized, it should get dispersed. Okay, to get dispersed, there should be someone who can pull this electron. If R group is an electron withdrawing group, then the negative charge will get dispersed, it will become more stable. If the R is electron donating group, then negative charge density will increase, it will become unstable. So whereas in the case of formate ion, this HC double bond O, O minus, there is no donation taking place. Whereas here, there is a donation taking place. So hence it will destabilize this anion. So hence this is less stable. So this is less stable, hence this is less acidic. That is reflected with the help of the pK values also. So this is one of the factors that will affect the pK value. That is the stability of the anion form. If the anion formed after releasing a proton is more stable, then the corresponding acid will be more acidic. Okay, for example, let us take some other examples also. Okay, if there is an electron withdrawing groups, if there are some electron withdrawing groups if are present, then how the acidic nature will change, let us see. For example, if you take this CH3 C double bond OOH, its pK value is 4.76. If you take this CH2 C double bond OOH iodine is there, its pK value is 3.15. CH2 C double bond OOH Br, its pK value is 2.86. Look at this. As the electronegativity of the atom attached increases, so these are halogens. Halogens have tendency to pull electrons. So this will pull electrons. If this pulls electron, what happens? The anion formed will be more stable. Okay, so this will after releasing a proton, this will form this anion. So here the electron gets delocalized, as well as halogen will pull this electron because it is an electron withdrawing group. Hence the negative charge gets dispersed. So hence this becomes more stable, hence this is more acidic. That is reflected with the help of this values also. Okay. Similarly is the case for bases. What is a base? A base is a substance that generally donates an electron pair. Okay, a base is a substance that donates an electron pair. So acid is a substance that accepts an electron pair. Let's take an example of this. Methylamine and ethylamine. What is a base? A base is a substance that, according to Laurie Bronsted, it accepts a proton. So if it accepts a proton, it forms CH3 NH3 plus. This will form CH3 CH2 NH3 plus. NH3 plus. So for bases, we generally use pKb values. Instead of going for pKb values, we can predict the acidic nature, basic nature, based on the pK of this. So pK of this is 10.7. The pK of this is 11. Now, so smaller the pKa, stronger is the acid. So that means this is strong acid as compared to this. And you know one thing, that stronger the acid, weaker will be its conjugate base. Stronger the acid, weaker will be its conjugate base. Okay, or vice versa. Weaker acids will have stronger conjugate bases. Okay, so protonated methylamine is a stronger acid than protonated ethylamine, which means that methylamine is a weak base. So here this is pK, based on the pK value of this also you can predict. See, pK value of this is 10.7 and this is, so out of this, smaller the pK, stronger. So this is a strong acid. If this is a strong acid, then its conjugate base will be weaker. So methylamine is weaker base. Okay, so one of the factor that affects the pK value is the stability of the anion. There are other factors also that affect it. One is the electronegativity as well as the size. Let's take an example. Let's take an example of CH4 NH3 H2O and HF. This is along the plate: carbon, nitrogen, oxygen, fluorine. As we move, electronegativity, what happens? Increases. Now, CH3, if it loses a proton, it forms CH3 minus. NH3 releases a proton to form NH2 minus. Water releases a proton to form OH minus. HF releases a proton to form F minus. So CH4 will release a proton to form CH3 minus. NH3 releases a proton to form NH2 minus, water releases a proton to form OH minus, and HF releases a proton to form F minus. So if the anion formed is more stable, then given acid will be more acidic. So stability of anion will decide. Now stability of the anion means its ability to bear the negative charge. So out of these, which can bear the negative charge easily? Fluoride can bear the negative charge easily because it is more electronegative. So fluoride can easily bear the negative charge. Since fluoride can easily bear the negative charge, it is more stable anion. If the anion is more stable, then this is more acidic. Okay, so hence HF is more acidic. Here electronegativity plays a very important role. So along the period, as the electronegativity increases, the stability of the anion increases, and the acidic nature of the substance increases. If you move down the group, if I go from HF to HCl to HBr to HI, after releasing a proton, it forms F minus. After releasing a proton, it forms Cl minus, Br minus, and I minus. The same case. That means if this is more stable anion, more acidic will be there. So which is more stable? If you consider a single atom, fluorine is a small atom, chlorine is a little larger, bromine larger, and iodine still larger. Right? So there is a negative charge here. So iodine can bear that negative charge easily because of its large size. So since iodine can bear the negative charge, so this is more stable. So since iodide is more stable, so HI is more acidic. So as we move down the group, electronegativity plays a very important role. As we move down the group, as we move across the period, electronegativity plays a very important role. As we move down the group, the size plays a very important role. So as we move down the group, the size of the anion increases, the stability of the anion increases. If the stability increases, the acidic nature of the acid increases. So HI is more acidic than HBr, HBr is more acidic than HCl, HCl is more acidic than HF. Whereas here, electronegative, they have almost, as we move, the size goes on decreasing also. So not much difference in the size is observed. So hence what happens is, here electronegativity plays a very important role. Greater than electronegativity, more stable will be the anion, more stable will be the anion, so the more acidic will be this compound. Okay, so this was about the strength of acid and bases. Thank you.